In the vast theater of the universe, everything begins with the smallest fragments of matter, objects so minuscule that they escape even the most powerful microscopes. The journey from the tiniest known entities to the largest cosmic structures is not merely a question of size, it's a story of scale, energy, and the limits of human understanding. At the very bottom of existence, far smaller than an atom, lie quarks and leptons, the elementary particles that form all matter. A quark is just about 10⁻118 meters across, so unimaginably small that if an atom were the size of the Earth, a quark would be smaller than a single house on that planet. These quarks combine in triplets to form protons and neutrons, the building blocks of atomic nuclei. Electrons, which orbit those nuclei, are even stranger, fundamental particles with no measurable size, treated in quantum mechanics as point-like entities.
Welcome to Beyond the Stars.
If you enjoy exploring the mysteries of our universe, don't forget to subscribe for more deep space discoveries. Atoms, formed from these components, average about 1/10 of a nanometer in diameter. That's 1/1000th of a meter, the scale where quantum rules dominate and classical intuition collapses. Hydrogen, the simplest atom, consists of just one proton and one electron. And yet this simple combination would later form the bulk of stars and galaxies. Combine atoms together and molecules arise. A water molecule, for instance, is only 0.27 nanometers long, yet its ability to form hydrogen makes it the architect of life. Biological complexity begins from such tiny structures: proteins, DNA strands, and cells emerging from molecules' endless capacity to arrange and react. A human cell, compared to the molecular world, is enormous, about 10 micrometers across. Within it, mitochondria generate energy, ribosomes build proteins, and DNA, coiled tightly inside the nucleus, stores the blueprint for life itself. Each strand of DNA, if stretched out, measures about 2 meters long, yet it fits inside a nucleus smaller than a speck of dust. When these cells gather, they form tissues and organs, and eventually an organism like a human, about 1.7 meters tall on average, a biological structure made of around 37 trillion cells. On this scale, humans dominate their environment, but in cosmic terms, they are still invisible. Move upward, and we encounter the vastness of our planet. Earth's diameter measures 12,742 kilometers, vast compared to human scale. Yet the Earth itself is only a minor world, orbiting an average star. From the surface, mountains like Everest seem towering, but if Earth were the size of a billiard ball, those mountains would be too small to feel. The oceans, stretching across most of the surface, hide the deepest trenches, Mariana Trench reaching about 11 kilometers down, but even that is thinner than the skin of an apple relative to the planet's size. Earth's structure is a layered sphere, an iron-nickel core at the center, a mantle of hot silicates above it, and a fragile crust on top where all life clings. Just 384,000 kilometers away, our moon orbits silently. Though small compared to Earth, only about 1/4 its diameter, it exerts a gravitational influence strong enough to control the tides and stabilize the planet's axial tilt. Its surface, pockmarked by craters and ancient lava plains, records billions of years of cosmic bombardment. The moon's apparent brightness has guided human mythologies, calendars, and exploration. Yet, in space terms, it's just one of hundreds of moons scattered through our solar system. Beyond Earth's orbit lies Mars, then Jupiter with its colossal size, about 143,000 kilometers in diameter, making it large enough to fit more than 1,300 Earths inside. Its atmosphere of hydrogen and helium rages with storms, including the Great Red Spot, a hurricane-like vortex larger than our entire planet that has persisted for centuries. Orbiting Jupiter are its moons, each a world of its own. Ganymede, the largest, is even bigger than Mercury. Further out, Saturn reigns with its breathtaking rings made of ice and rock, stretching hundreds of thousands of kilometers wide, yet only a few meters thick. Uranus and Neptune, the ice giants, complete the visible boundary of our solar system, each surrounded by faint rings and moons frozen in eternal cold, but the Sun dominates them all. With a diameter of 1.39 million kilometers, it holds 99.86% of all the mass in the solar system. Inside its core, temperatures exceed 15 million degrees Celsius, fusing hydrogen into helium and releasing energy that sustains life on Earth. Every second, the Sun emits more energy than humanity has consumed in its entire history. Still, our star is modest by cosmic standards. There are supergiant stars like Betelgeuse, about 764 times the Sun's radius, and Ui Scuti, which would engulf the orbit of Jupiter if placed at the center of our solar system. These stars burn brighter but live shorter lives, eventually collapsing or exploding as supernovae that forge heavy elements, the same carbon, oxygen, and iron found within us. Beyond individual stars lie the stellar nurseries and nebulae, vast clouds of gas and dust where new stars are born. The Orion Nebula, 24 light-years across, glows with the energy of newborn suns. Even larger are the remnants of exploded stars, such as the Crab Nebula, expanding outward at thousands of kilometers per second. Step further, and we reach the scale of star systems and clusters. Our Sun is one of an estimated 400 billion stars in the Milky Way galaxy, a spiral disk 1,000 light-years wide. Within this galaxy, stars orbit a supermassive black hole called Sagittarius A+, 4 million times the Sun's mass, hidden at the center. Despite its name, a black hole is not an empty void. It's a region where gravity becomes so extreme that not even light can escape. Space and time warp around it, and anything crossing its event horizon is lost forever. Our galaxy is not alone. The Milky Way belongs to a local group that includes the Andromeda Galaxy, which is larger, about 220,000 light-years across, and moving toward us at 110 kilometers per second. In roughly 4 billion years, the two galaxies will merge into a single, massive elliptical galaxy. Surrounding them are smaller dwarf galaxies, orbiting like satellites around these giants. Beyond our local group lies the Virgo supercluster, a gravitational collection of thousands of galaxies, stretching over 110 million light-years. Yet even this is just a small section of an even larger network of light-years, where galaxies form along vast filaments of dark matter and gas, separated by immense voids almost entirely empty. Each filament resembles the strands of a vast three-dimensional web, and every intersection holds clusters containing thousands of galaxies. The largest of these known structures, like the Hercules Corona Borealis Great Wall, extend over 10 billion light-years, so large that light itself takes most of cosmic history to cross them. If we try to comprehend this scale, we must remember that 1 light-year is about 9.46 trillion kilometers. The observable universe, everything light has had time to reach us since the Big Bang, is roughly 93 billion light-years across. Within it, scientists estimate there are over 200 billion galaxies, each with hundreds of billions of stars. And beyond that, we do not know. The universe may extend infinitely or may curve back on itself. Our current horizon is not a boundary of reality, but simply the edge of what we can see. To grasp the vastness, imagine shrinking the entire universe into a sphere the size of Earth. The Milky Way would then be smaller than a single atom. This staggering scale reminds us that everything we experience, our planet, our lives, our history, exists within a barely perceptible fraction of cosmic reality. Yet it also reveals how matter organizes itself across scales, from quarks forming protons, to atoms forming stars, to stars assembling galaxies, and galaxies weaving the universe itself. This hierarchy of structure follows patterns of physics, gravity pulling together the large, and quantum forces governing the small. Between them lies everything familiar. Stars burn because quantum tunneling allows fusion to occur. Planets form because dust grains stick through electrostatic forces before gravity takes over. Life emerges because chemistry thrives at the balance between these extremes. The universe is, in essence, a continuum from the nearly infinite smallness of subatomic particles to the almost boundless vastness of cosmic walls. And while humans occupy a middle ground, our minds reach far beyond it. Through telescopes and particle accelerators, we've stretched perception both inward and outward, observing the birth of galaxies and the collisions of subatomic particles alike. Each new discovery shifts our sense of proportion. Once, Earth was the center of creation. Now, we see it as one of countless worlds orbiting countless stars. Our galaxy, once thought unique, is one of hundreds of billions. Even the universe we observe may be one of many, an idea hinted at by theories of inflation and quantum cosmology. The universe's origin, the Big Bang, began as a singularity, a point smaller than an atom, where space and time themselves emerged. From that instant, 13.8 billion years ago, the universe expanded and cooled, giving rise to particles, then atoms, then stars in galaxies. Even now, that expansion continues, driven by mysterious dark energy that pushes galaxies apart faster and faster. About 68% of the universe consists of this dark energy, 27% of dark matter, and only about 5% of the ordinary matter that forms everything we can see. In other words, nearly all of existence is invisible to us. Still, from that small visible fraction, the cosmos has evolved into something of breathtaking scale and beauty. We have mapped cosmic balance, microwave background radiation, the faint afterglow of creation, and traced it to the very first moments of time. We've detected gravitational waves rippling through space-time, caused by colliding black holes. Each discovery confirms the same truth. The universe is both vast and interconnected. The smallest particles and the largest structures obey the same fundamental laws. And when we step back to view it all, from quarks to galaxies, from the atom to the observable universe, it becomes clear that scale is relative. The tiniest things define the largest, and the largest give meaning to the smallest. We, too, are part of that chain, built from atoms born in stars, living on a planet that orbits one among billions, within a galaxy that drifts through an endless cosmic sea. In the grand hierarchy of existence, our size may be insignificant, but our capacity to understand it is not. Through that understanding, the universe becomes not just vast, but knowable, a story written in space and time, waiting to be told. The universe still holds countless mysteries waiting to be uncovered. Subscribe and stay with us as we continue the search.